Recording. All right. Good morning, gentlemen, whoever is watching this video. Good morning to you. I hope we had a good weekend and we're ready to learn some circular motion, work, and energy. This is our third unit coming up. All right. So we're halfway there. So let's keep on trucking. All right. So unit 3, unit C is circular motion, work, and energy. Okay, so you would have briefly learned about work and energy during Science 10. Okay, circular motion is going to be kind of a new concept that we're going to be talking about. This ties in with unit 2 quite in some regards, because we are still going to be dealing with friction and force of gravity and the normal force. So you guys are pretty familiar with that already. So hopefully this week's content can kind of help us kind of tie in all of these units together. Okay, so chapter 5, what we're going to be starting today is using Newton's laws to explain circular motion. Okay. So defining circular motion, generally speaking, this is kind of anything that is moving in a circle. Okay, so in these couple examples here, we have a yo-yo being rotated on a string. Okay, we'll notice that as it rotates around the circle, its position and the direction of its velocity is constantly changing. Okay, if we were to be rotating a ball on a string, and if it were to break off at any point, it would fly off at a straight point. We call this the tangent line. Okay, we're going to talk about that a little bit later. But yeah, so it's going to fly off right on a tangent line. And if not, because we have the force of tension of the ball on the string, if it's not going to break, it's just going to continue in the circular motion if we continue to move our hand in that motion. Yeah, so if you look at over here on the right, or on the left, sorry, we'll see that we have a velocity kind of going off on a straight line. Again, this is called the tangent line, okay? And then if you look right here where the man is spinning it from the top view, we have force is equal to the mass times acceleration, and that is pointed to the center, okay? That is referred to as centripetal acceleration. This is any acceleration that is directed towards the center of a circle. Okay, so circular motion, the definition of circular motion is a movement along an object, movement of an object along the circumference of a circle, or rotation along a circular path. Okay, so tying into our math class, remember circumference is the complete distance around the outside of a circle. Okay, so as an object moves along the circumference of a circle, or rotation along a circular path. Okay, that is circular motion. It can be uniform with a constant angular rate of rotation. So just saying that it's rotating in a circle at a constant rate. Okay, so uniform circular motion. Or it can be non-uniform with a changing rate of rotation. So this is going to be if we're slowing it down at some points and it's slowing down at others. Okay, if it does not have a constant speed, we consider that non-uniform circular motion. So just take a moment here to kind of think about some things in our lives that have circular motion. Okay, so some examples of this could be, oh, don't want to spoil the surprise. Some examples of this could be driving a car, turning a corner. Another example of this could be a merry go round, ride at an amusement park, a Ferris wheel, roller coaster, a string, orbiting planets, to name a few, okay? And anything that has circular motion, anything that is like turning or rotating in a circle, this is circular motion, okay? So those are some examples of that. I just lost my cursor, so give me 1 second here. Oh, sorry, sometimes when I go to like text to annotate, I lose my cursor. There we go, I found it again. All right. Excuse me. And okay, so again, just to kind of reiterate some examples of circular motion that we see in our lives. So the sun and the planets all orbit in pretty close to circles. They actually orbit in ellipses, but we'll talk about that a little bit later on. For the sake of today, we're going to say that sun and the planets orbit in circular motion. The Earth and the Moon, same thing. We have atoms and electrons that will, well, these are examples of circular motion because as the electron orbits the nucleus, it does so in a circular manner. An example of circular motion could be some person running around a running track, or circular motion as experienced on a Ferris wheel. Okay, so lots of examples of circular motion in our everyday lives. Just to present a few. All right, here is a video kind of introducing and discussing uniform circular motion. Due to copyright issues, I can't actually play this video on my video and then add that up to YouTube. So I'm going to need you two students to go ahead and watch this on your own time. I will include the link of this video on the Google Classroom when I post this lesson as well, okay? So I'll just put that one on pause for now. And that's a really good one just for introducing circular motion and stuff like that. Okay, next we kind of have an interactive here, and I would like you to kind of play around with this on your phone. So if you go ahead and click the link, so let's just see what I'm sharing with. Okay, here we go. So here is just like a little interactive for circular motion. So click the link and kind of play around with it. There is a little exercise associated with that as well. So if you click on the exercise, you will see a 3-page handout here. So please complete that today. This is not for marks, but it's just going to kind of help us reinforce what circular motion is and what is going to occur as we play around with this kind of interactive here. So here is the interactive, and with it, we can change the speed of it. And as we change the speed, we'll notice that the acceleration and the net force is changing. Okay, we can also influence the size of the radius and the mass of the rotating object. Okay, so here is the interactive itself. I'd like you guys to take the time to go through and complete these practice problems here, okay? And you should just be able to click the link right on the PowerPoint. All right, so back to here. So yeah, so you guys can either enter this link into your phone or click on it on your computer, whichever works for you, and then go and complete the handout, please. Okay, so now we're going to kind of analyze this image of is what we're going to consider a bob. Okay, so a bob is usually, sorry, I'll just stop moving you guys. There we go. A bob is kind of a general term for anything that is attached to the end of a string and is rotated around. We're going to call that a bob. Okay, so on the image on the left, we're going to, or on the right, sorry. So we have a bob on the end of a string, and just imagine that this is rotating and rotating and rotating. Okay, so this ball over here is going in circles, in circles and circles. Okay. Now, if the red location is A, and sorry, I'm just going to draw on here. So if this is position A and position B over here, okay, if we are rotating the bob at a constant speed in uniform circular motion, if we compare the speed of the bob at the two locations, it should have the same speed. Okay, remember, speed is a scalar quantity, so it only has a magnitude, so how fast it is going, and no direction. Now, if we compare the velocity of the bob, if we look at point A, we'll notice that the velocity of the bob is pointing straight to the right. Okay, and then a moment later, it is pointing to the right and down. So the velocity has changed because the direction of the bob has changed. Even though it's still rotating in a circle, the instantaneous velocity at point A and point B are different. So the velocity is going to be different at these two locations. Okay. I just lost my cursor again, so give me a second. There we go. Perfect. Okay. Okay, so this is just kind of a summarize to the last slide. So the bob has the same speed throughout the motion, but the velocity, so the magnitude and the direction, is constantly changing. At the top of the circle, the instantaneous velocity of this bob is to the right, and a moment later, the instantaneous velocity of the bob has changed to the right and down. So the velocity of an object moving in a circle is the tangent line at the point, so it's perpendicular to the radius. So if we look at point A, the radius is at a straight up and down, it's just straight up and down, and then the velocity is going to form a perpendicular line to the radius. So we're always going to have a right angle right here. Okay. So this brings us to centripetal acceleration. So remember, centripetal is center seeking. So centripetal acceleration is acceleration that is pointing to the center of the circle. So if we are looking for the change in velocity between these two vector arrows, so remember at point A, there we go. So at point A, remember the instantaneous velocity was going something like this. Okay. And then here we're at point B, where the instantaneous velocity was something like this. Okay, so like we've been doing before, we can create a resultant vector to show us the change in velocity of the two velocities, of the instantaneous velocities at point A and point B. Okay, so this is what the instantaneous velocity looks like at V1, and here's our instantaneous velocity at our VF. If we flip the direction of the initial velocity, so if we are saying right is positive, we're just going to flip that velocity vector. So now it's in the negative direction, okay? So, and we're gonna leave our VF alone. So our VF velocity is pointing this way, our instantaneous, or our negative initial velocity is pointing back to the left. So our resultant velocity is right here. It's pointing to the center. So remember, the change or acceleration is the change in velocity. So if we have the change in velocity, which is pointing towards the circle, this will give us centripetal acceleration, okay? So again, centripetal acceleration is just a acceleration that points to the center of a circle. All right. So as we just kind of alluded to, centripetal acceleration is the acceleration acting towards the center of a circle. It is perpendicular with the instantaneous velocity, so it's kind of similar to the radius in that aspect. And it usually or oftentimes will point in the direction of the force causing it. So if we look at the example of this person swinging around a shot put, not too sure what that is. I know shot put, hold up like this. Anyways, so this athlete here is spinning the ball on a string. The centripetal force and the centripetal acceleration is pointing to the inside of the circle, or the source of the force. Okay. According to Newton's second law, if a mass is accelerating, it must also experience a net force. So in this case, we're going to call it a centripetal force. Okay, so just like a centripetal acceleration, it's a centripetal force. It is pointing to the center of the circle. Okay, centripetal means center seeking. Here is the formula for centripetal acceleration. You will find this on your formula sheet that you guys have been using for the semester. Okay, so we have centripetal acceleration, AC, in the units of meters per second squared, because it is acceleration, is equal to the velocity squared divided by the radius of the circular path. Now remember, the radius is only half of the diameter. That's a circle. Okay, so if this, here's the center of the circle. Okay, looks like a pokeball. So this whole thing across would be the diameter, and just half of it would be the radius. Okay, so remember, radius is just half of the diameter. And yeah, so if you're looking for the centripetal acceleration and you're given the velocity and the radius of the thing that is rotating in a circular fashion, you can calculate the centripetal acceleration using this formula. Okay, so now we're talking about centripetal force. This is a net force that will act on an object to keep it moving or make it moving in a circular path. In circular motion, the direction of the acceleration points to the center of the circle. This means that the force must also point to the circle. Okay, here are our same images from last slide. If you wanted to calculate the centripetal force. It's going to be using this formula, except it's going to look slightly different. So it'll be Fc is equal to the mass times the centripetal acceleration. Okay, so centripetal force is equal to the mass times the centripetal acceleration. Okay, you guys have this formula on your formula sheet. A is equal to F net over M, and just with a simple substitution is going to become AC, so centripetal acceleration, is equal to the centripetal force divided by the mass of the object that's rotating. And just wanted to clear up a potential confusion. So the centripetal force is not a special force that's responsible for circular motion. It's more of like a general term given to any force that acts towards the center of a circular path. Okay, so if we're in a car and we're turning a bend, okay, we're not like turning the bend because of some magic centripetal force. When we get into the practice problem later, we'll talk about this again, but it's the friction of the tires that's acting on the road that causes us to turn. So just a little teaser for some of the problems that we're going to cover later. I lost my cursor again. There we go. So just a little teaser. If we are going around a corner in a car, so the centripetal force of that car moving is going to be equal to the force of friction. Okay. And again, maybe put a star beside that one. We're going to solve that later on this week. All right, here is another good video. I will include the link on the Google Classroom, and this is just going to kind of summarize and go over what we have kind of introduced today. Okay, so as we discussed earlier, the centripetal force is not some magical force that is just there that makes an object rotate in a circle. The centripetal force is a generic term used to describe whatever force that is keeping that ball or the bob or that object rotating in a circle. So in this case, we have a bob on a string that's being rotated around. So the question is, what is the cause of the force? What is the cause of the centripetal force on the ball? So what is the force that is acting on the ball to move in a circular motion? So think about that for a second. What is causing the ball to move in a circular motion? Okay, so in this case, the force that is causing the ball to move in a circular motion is the force of tension exerted by the string. Okay, so the tension in the rope is the cause of the centripetal force on this ball. So our next question here, what is the cause of the centripetal force on Earth? What is causing the Earth to rotate in a circular motion, even though it's an ellipse? But for the case of today's class, it's a circular motion. Gravity. What is causing gravity? Yeah, gravity from the sun. Perfect. That's excellent. Okay. So in this case, gravity from the sun is acting as the centripetal force on Earth. Very good. All right. So that's it for today's lesson. This is just kind of an introduction to centripetal forces and circular motion and that kind of thing. So is what you guys have to do for today now is complete the interactive handout. So if we jump back to this guy right here. So go onto this website, play around with the interactive there, and then answer the appropriate questions that were related to that. It's right on the link there. So that is your one assignment. And then there's also going to be a 5.1 practice problem assignment, okay? So I will again email the link out there, or the document. It will be in the Google Classroom. And if you have any questions as you go and are working through that, please send me an email or a text. I'd be more than happy to help you out. All right, so I'm going to end the recording now. So I hope you guys enjoyed the lesson, and we will see you next week for sure. Thanks. Hey guys, okay, the video's done now.
It's still recording.
Oh yeah, it is.